On behalf of the members of the Academy, welcome to this episode of Learning and Living STEM in Connecticut, the podcast of the Connecticut Academy of Science and Engineering. My name is Tan Deleon. I'm an elected member of the Academy and serve as an officer for its governing council. For more information about the Academy, visit ctcase.org. That's ctcase.org. Our topic today is the future of aircraft propulsion. Here to discuss what we should know about this and what is happening in Connecticut is Dr. Michael Winter, Chief Scientist at RTX, which is comprised of three industry-leading businesses, Collins Aerospace, Pratt Whitney, and Raytheon. He is also a member of the Academy. Welcome, Michael. Can you tell us a bit about your role at RTX and your career in engineering?
Sure, thank you. And thank you so much for this opportunity. I'm the chief scientist at RTX. I started first with a bachelor's in mechanical engineering and then a PhD from Yale in engineering and applied sciences. And I've been with the company, now RTX, Legacy United Technologies Corporation, for just about 40 years. I started fresh out of school in the corporate research center and have moved around the corporation over that time in various roles, all technical, all focused on technology, and mostly in the aerospace realm. As the chief scientist, I'm responsible for the technical integrity of our technology portfolio, number one. Number two, to accelerate those technologies. And number three, to represent those technologies externally. In the time that I've been active in the field, I've published over 50 papers and authored more than 40 patents. I'm also not only a member of CASE, I'm a fellow in the American Institute of Aeronautics and Astronautics, as well as a fellow of the Royal Aeronautical Society.
Oh, wow. You have a very impressive resume, Michael. So thank you so much for taking the time today to speak to us. I know our listeners in Connecticut are going to be very privileged to listen to what you have to say. So just to get into it a bit, for our listeners who may not be familiar with RTX, can you give us like an overview of the business?
Sure. So RTX is one of the largest aerospace defense companies in the world, with our three divisions, Collins Aerospace, Pratt Whitney, and Raytheon. We really supply most of the subsystems across the aerospace domain. In fact, every second of every day an airplane takes off with our content on board. RTX is about at $80 billion in sales last year, about 185,000 employees worldwide. We have 17,000 employees right here in Connecticut, and we have about 57,000 engineers in the company. Those engineers represent about 60,000, a little more than 60,000 patents. And in a given year, we typically spend of order $7.5 billion in research, development, and in engineering. That's both our money as well as customer money. Just a little bit more about Collins Aerospace. We make all the subsystems on the aircraft. Everything from the lighting systems, the electrical systems, the landing gear, through the galley, the slides, the emergency slides, the cockpit systems, really everything that allows the aircraft to function, we provide that at Collins Aerospace. At Pratt Whitney, we are a premier provider of propulsion systems. From the very smallest, we make missile engines, through turboprops, helicopter engines, and business jets, up through commercial airliners, as well as military platforms, including the premier in the United States Air Force, the F-22, the F-35, the B-21 bomber. And Raytheon, we hear a lot about Raytheon in the news today. We make the missiles, the radars, the radios, the sensors and seekers that are enabling defending freedom around the world today.
Oh wow, yeah. So it's a logical step that these businesses are under the umbrella of RTX because they pretty much supply one another and complement one another. So yeah, thank you for that explanation, Michael. So with respect to Pratt and Whitney, there's a long history in Connecticut for that company. Can you expound upon that a bit, like how it got its start, etc., just for folks that are from the state and may not be familiar with the history of Pratt and Whitney.
Sure. So I'm proud that I've spent more than 20 years at Pratt and Whitney in various leadership capacities. Pratt & Whitney is celebrating its 100th anniversary this year. In 1925, Frederick Renzler had this idea that he actually saw others starting to develop in other parts of the world, that if you took the engine, these were piston engines, much like in an automobile, where the pistons go back and forth in a box. The box has a water jacket around it. That was what was powering aircraft up until that point in time. And what he wanted to do was take the engine and take each piston and make it stick out radially, put a heat exchanger around it, so that each piston essentially became its own radiator heat exchanger to allow for removal or elimination of the water cooling. That got rid of the pumps, that got rid of the water, got rid of a lot of the metal, and with that you can increase the thrust to weight, which is a really important parameter when it comes to flight, by a factor of about 2.5 to 1. So he took that idea to Pratt and Whitney Tool and Die. They gave him some backing and some space. Actually, we just unveiled a plaque at the original site on Capitol Avenue in Hartford just a few weeks ago to designate it as an historical site. And it's important to note that when he did this, it was a re-architecture of the engine. It was not just improving on a particular set of technologies, but it was the systems engineering to change the topography of how the engine was arranged. We went on to make over 500,000 of these engines during World War II. Now, if you sort of look through after the war, the order book obviously significantly diminished. And so Pratt & Whitney was a little bit out of position because we were not allowed to work on the gas turbine technologies that had emerged during the war, particularly in the UK and in Germany, that was somewhat transformative. And so we had to catch up. And so what we did at Pratt & Whitney was, again, reconceived a new approach where re-architecting not just changing and putting in technologies, but re-architecting it, re-system engineering it, so that there were essentially two parts to the engine. In the core, which spins very fast on a shaft, you've got a compressor, a combustor, and a turbine. And then adding in a long shaft that goes through the middle and put another low pressure turbine on the back and a fan in the front that allowed you to have that spin at a slower speed. And what that did in the late 1950s was introduce an engine both for military and commercial that enabled the economics really that set forth the dawn of the jet age and the launch of the Boeing 707. Those technologies continue to mature, and further improvements in the efficiency of the engines in particular were introduced. And again, in 2015, 2016, we introduced a new technology, again, a re-architecting of the engine, which was what's called a geared turbofan. And what that did was it slowed down the fan even more than just the amount that big long shaft allowed you to do. And that lets you get the optimal efficiency on the fan but let the turbine in the very, very back spin at its optimal speed. And by doing that, we were introduced about 16 to 20% improvement in the fuel efficiency of the engine. Huge impact on the economics, but also by slowing down the fan, the engine became much quieter. It turns out that most of the noise comes from the tips of the fan blade, little shock waves or sonic booms coming off the tip. And so we were able to quiet it down by about noise footprint by 77%. Significant change. And so as we look to the future, we're not just infusing new technologies, but we have new technologies that we are preparing that will, again, allow us to re-architect the engine.
Wow, that's quite the history for Pratt and Whitney. And it just shows, like to our residents of Connecticut, the power that the industry that resides here in the state has, and the effects, the long-lasting effects it has uh, for uh, for the history of jet aviation. So before we start discussing the future here, can you just ground us and give us some of the fundamentals of jet engine design, for those that are not familiar with the different pieces that need to come together in order for flight to take place? That would just help us going forward.
Sure. So I would submit that a gas turbine engine, a jet engine, is the most sophisticated mass produced device known to humankind. Inside, there's up to 40,000 parts. The parts are spinning at tens of thousands of RPM. And some of those parts, the turbine blades or the compressor blades, are moving on the inside of the case, literally within a hair's breadth of parts that are not moving. Tens of thousands of RPM. Just think about the tolerances that need to go into that. Now, what happens in the engine? Uh, there's the fan in the front, and that's much like a propeller on other types of airplanes. It pulls the airplane forward, particularly in commercial applications, particularly at lower altitudes. That's really the part that provides most of the thrust. And the rest of the engine is really designed and defined to provide that power to make that fan do what it needs to do. Behind the fan, there's a low pressure compressor. And remember I said that's on a big long shaft tied to a turbine in the very back. And that spins at thousands of RPMs. And then most of the air actually goes straight through the engine. That's called a high bypass engine. The reason you do that is because you get more propulsive efficiency. So like a propeller, propulsive efficiency by just letting the air go straight through. But a small fraction of the air, like 1/12 or 1/13 of the air in a typical commercial engine today, gets pulled in to the very core. And there's a compressor that squeezes that air and raises the pressure. And as you raise the pressure, much like your bicycle pump, it gets hot. And you go through successive stages so that by the time I get to the back of the compressor, the air is really hot. It's hot enough to melt rocks. And then what do? We dump in fuel and we light it on fire. So it gets even hotter, and that happens inside the combustor. That's where the fuel is actually consumed. Literally, literally 10 plus gallons a second of fuel can be consumed when the throttle is pushed forward. And then the hot gas exits the combustor and goes into the turbine, which starts to spin. And that turns that motion into motion on a shaft. And that's what really drives that compressor that you heard that I mentioned before, the one in the front. And then behind that, there's another turbine, and that's the one that drives the fan. Two other points of note. Number one, those turbine blades, remember I said they're spinning at tens of thousands of RPM. They could be the size of my hand. The pull load on a turbine can be equal to the weight of an entire fighter airplane. So inside, and then the temperatures at that point in the engine are hot enough to melt all the metal surrounding it. Don't think about that next time you're on an airplane. And to keep it from melting, what we do is we take some of that air that was hot enough to melt rocks. That's our cooling air. We circulate it inside the turbine blade. It is the world's most sophisticated heat exchanger. And in the blade, there's drilled into it tens of thousands, sometimes of little holes. So the air fuses out like an air hockey table. So the hot gas can never touch the surface. Last point I'll make is we do much of the engineering and much of the manufacturing of these products right here in Connecticut, in East Hartford, Connecticut, in Middletown, Connecticut. We build the military engines, the commercial engines that I'm describing, and we have 11,000 employees at Pratt Whitney here in Connecticut.
Wow, that's I mean, when I listen to you explain the fundamentals, it's mind blowing how impressive that a jet engine can be. And you're absolutely right. You know, if definitely don't think about it when you're on when you're on a plane flying somewhere. But that's very very impressive. Thanks for that explanation. So. So I guess like what are the key areas RTX is working to advance propulsion technology into the future?
So propulsion efficiency is really the key. And part of that is, of course, the role in the environment, but it's also about economics. 30 to 40% of the cost of running an airline is fuel. 30 to 40% of the cost of running a modern air force is also fuel. And when we think about some of our near peer adversaries, for instance, across the Pacific Ocean, we also have to think about those efficiencies in terms of range and logistics. And so efficiency is king. Now, there's really two elements that go into the efficiency of the engine. I already mentioned the propulsive efficiency, which is what happens with the fan and that bypass duct and the nozzle in the back. And by introducing the geared turbofan, what we really did was we differentiated ourselves on the basis of that propulsive efficiency. The other part of efficiency is thermal efficiency. And the overall efficiency of the engine is the propulsive efficiency multiplied by the thermal efficiency. The thermal efficiency is exactly what it sounds like. It's the energy release of consuming the fuel, making that into thermal energy, and then translating that into motion on a shaft. Okay, that's what the thermal efficiency is. And in order to do that, to achieve those efficiencies, thermal efficiency, typically in order to get higher efficient from a thermal standpoint, when I burn something, I have to go to higher pressures and temperatures. Now, as you heard, we already are kind of pushing the limits of the material systems. And if you look at where we've been since the dawn of the jet age, Von Ahn and Whittle, 87 years ago, when they first invented the gas turbine engine, we've improved by about 400 to 450% in thermal efficiency. And we're really running up against what are the limits of these material systems, such as metals. And so the key opportunities to go to even higher thermal efficiencies are either to go to more advanced cooling inside the blades. And we're doing that. We recently built a major factory, almost $1 billion investment in a factory that will be able to make these blades with ever more intricate inside as well as the aerodynamics on the outside and the whole drill, and to do all of that under a single roof, as well as advanced material systems. And we're making the appropriate investments in things like ceramic matrix composites and other material systems that let us go to higher temperatures. So by combining that, we see an opportunity to go to improve the engines both in thermal and propulsive efficiency. But that's not enough. So we will also need to reach for hybrid electric, and I can talk more about hybrid electric as an opportunity. And then the other thing to do is to look at the fuels we burn. We currently use synthetic aviation fuels. These are fuels made from sewage or garbage, and that's particularly important, especially here in Connecticut, where we do have a significant trash issue. But it can also, these fuels can be made from agricultural cover crops and the like. And so that's a significant opportunity, as well as other fuels that don't carry carbon atoms and can be made renewably, things like hydrogen. And so we're actively working on that as well.
Okay, that's quite the list of things that you guys have on in the hopper. You did mention hybrid electric propulsion, and yeah, if you can expound upon that a bit, that'd be great. But in that vein, also, what about fully electric aircrafts? Is that a thing, or is that just like a fantasy?
So if I look at the energy stored in a battery compared to the energy stored in the equivalent mass of jet fuel, that amount of energy is about 1/40th. So since mass is so important for flying machines, which is what we power, that really is a significant challenge for all electric flight. You can do a few passengers, a few kilometers. We do have partners that are working on all electric aircraft for trainers, but you're talking about a flight with two people on board, not a pressurized cabin for a half an hour flight, when you consider the reserve, for example, that's required to go anywhere. And so, really, not very practical. Also, note that to put it onto an airplane, you have to take those battery cells and put them in a box. The box has to be fireproof. It needs to have current management. You need to put on thermal management. All that adds more mass. And again, mass is the enemy when you want to get off the ground. So all is not lost, and we see value in a hybrid electric. And it's not about arbitrage per se, meaning we're not replacing the fuel we burn with the batteries that are charged. We actually combine it and reimagine what the propulsion system looks like with this new set of effectors, these electrical effectors, the motors, the drives, the generators, the distribution systems, which, by the way, we make all of those components at Collins Aerospace for the entire aviation industry today. And so, together with Collins Aerospace and Pratt Whitney, we're again re-architecting what the engine will look like to be a cyber physical machine. So to do that, we actually have a series of demonstrators. We are looking at the all electric, and this is again just a couple passengers, a couple kilometers. We call this scalable turboelectric propulsion, or STEP Tech. And we've actually built up in East Hartford, Connecticut, at our research center, a what you would think of as a copper bird. So we have the entire propulsion system from the gas generator engine into the generator, into what we call the juice box, a big appropriate battery, with all the management systems and even propulsors sitting in a wind tunnel. So we can actually fly the entire mission. We then take those similar components and we are putting together, and in fact, we're about to assemble it into the airplane for a regional turboprop airplane. A regional turboprop, say a Dash 8-100, is 2,000 shaft horsepower on the ground. That's 2 megawatts. So imagine a 50-50 hybrid, 1 megawatt electric and 1 megawatt, which is the gas generator. And so we've now built this into an engine. We've run the entire mission profile. We just in June demonstrated that we can do full power for takeoff, greater than the 1,800 shaft horsepower required to generate to get off the ground. And we're now integrating that with our partners into an aircraft that we've actually procured for this purpose. We also are partnered with ATR, which is one of the world's largest manufacturers of turboprops, and we're helping them define what a hybrid electric propulsion system would look like for their next generation aircraft. We're also partnered with Airbus on a helicopter. And so basically this one now uses a 250 kilowatt electric system for a helicopter application. And we're building that. We call that the Pioneer Lab, and we're partnered with Airbus. But really, it comes down to most of the action is in the commercial airliners. And when you think about most of those are actually single aisle. So these are A320s or 737s. An A320, 737 roaring down the runway, 30,000 pounds of thrust. That's 18 megawatts. So what can I do with that megawatt, half a megawatt to a megawatt? Well, it turns out, remember I told you there's the two shafts in the engine? I put a motor starter generator on the core that spins at tens of thousands of RPM. I put another motor generator on the part with the fan and the low pressure turbine. And now I can move power back and forth between the two of them. And I use that to cover all the transients and all the off design conditions. And in fact, it turns out that it's most efficient to land with full batteries because as I'm approaching the airport, it's downhill. And so my throttle setting is not the most efficient place to run the engine. So I use that to charge the batteries and I can turn that into faster gate turn times. We are developing that into the engines we have on the A320 today. It's called Switch. It's a program we're doing with our partners, Airbus and GKN and MTU, and we're developing a demonstrator that we're going to run the engine and hopefully get that to flight test at some point later this decade.
Wow, that's yeah, you guys, that's quite the amount of technology that you guys have developed. So you did mention a term, and I just want to make sure uh, I understand what you said. You said cyber physical. So is that similar to like a digital twin, or is that completely different? Because I've heard digital twin before and more familiar with that.
So it's the machine. Every jet engine actually has a computer embedded in it.
Okay.
Okay, and that computer is fully controlling the engine. Think of the engine we make for the F-35 Lightning II aircraft. That airplane flies along, a fighter airplane that the United States premier aircraft, as well as 19 of our allies are or will be flying that airplane, flies along at Mach 1.6, stops, and could land vertically. The engine nozzle turns downwards. There's a shaft with a clutch. There's little jets of air that come out of the wing to hold the airplane in the air. That computer algorithm is incredibly sophisticated. We invented a whole new branch of applied mathematics to enable that. And literally more than 20 patents associated with that. And so those algorithms and that computer is an integral part of the actual machine. And so when I say cyber physical machine, that's what I'm talking about. Now, when I put electrical devices and I start moving the power flows within the engine itself, that's essentially think of the electrical system as just a new set of effectors that can exert huge amounts of power because the engine is such an incredible power plant. We then use that and we can optimize how in the mission the engine is operated to the utmost efficiency. For the turboprop example, we can achieve a 30% improvement in efficiency. And even with the single aisle application, the commercial airliner, right now, even with today's battery technologies and proven technologies, we can get of order 3 to 5% improvements right away, hopefully, perhaps in the next generation of aircraft.
That's definitely remarkable, and thanks for clearing that up. So moving on here. So if we were to, in recent years, you've seen a lot of talk about like using hydrogen as an aviation fuel, And I know you were talking about, the propulsion and thermoregulation, and we just spoke about, the hybrid electric and how phenomenal that is going to be from a game-changing perspective. Where do you see where does RTX stand on this technology with respect to hydrogen as an aviation fuel?
So, hydrogen is an interesting fuel. It turns out that we have a long history with hydrogen. If you look all the way back to 1956, the CIA figured out that the former Soviet Union had missiles that could reach up to 80,000 feet, which was where the U-2 was flying. This is long before Gary Powers was shot down in his U-2. And so there was a program in 1958 that was conceived by Kelly Johnson of Lockheed Martin Skunk Works that was called Project Suntan. And this was an airplane that would fly at 100,000 feet, but the air is so thin at those altitudes that you need to use hydrogen as the fuel. The use of hydrogen, it turns out, is very robust for combustion processes, but storage is a challenge. It also turns out on a mass basis, it has about 3 times the amount of energy as jet fuel, about 121 megajoules per kilogram. But it takes up 4 times the volume, and therein lies the challenge. So there's a few other challenges when I think about a commercial airliner. Obviously, in order to make the volume challenge, what you need to do is you need to store the hydrogen as a liquid. Now, the problem is liquid hydrogen is minus 253 degrees centigrade. That's really cold.
Yeah.
But there are other challenges. Number 2, when I burn hydrogen, I actually produce more oxides of nitrogen. Oxides of nitrogen are a regulated species. They are implicated in global climate. And so that represents another challenge. We also, if you look at on an equivalent thrust basis, when you burn hydrogen relative to jet fuel, it turns out you make 2.6 times more water vapor. Water is also implicated in changing the global albedo of the climate, as well as when I burn hydrogen, I could make with more water contrails. Contrails are the vapor condensation trails that you sometimes see behind airplanes. And under the wrong conditions, they trap the long wavelength radiation, essentially infrared or heat, between the ground and the sky. And that also can contribute. In fact, even though CO2 exists in the atmosphere of order a century, and the contrails only exist for, say, 6 to 10 hours, it turns out that the contrail can be as bad or worse than CO2. And so what we did at Pratt Whitney recently was we took all of this, we went back and studied what we did in the late 1950s with Project Suntan, where we actually ran a hydrogen-fueled engine. And we reimagined, again, the engine architecture to take advantage of all these challenges. So we took the cold of the liquid hydrogen, and remember I said it's too hot, right? So we used that for cooling. And we use that to condense some of the water in the exhaust and make steam. We take that water from the exhaust, the excess water, and we actually re-inject it as a cooling fluid into the engine. And that does 2 things. Number 1 is we know from the stationary gas turbine business that in order to control the oxides of nitrogen, by putting in water, you bring that down, the oxides of nitrogen generations dramatically. Number 2, if you look back at the old videos, all the way back to, say, the B-52 getting off the ground in the early days, they used to spray water in. The reason they did that was because you get more thrust out of the engine. So by putting in the water into the thermodynamics of the cycle, you can actually shrink the size of the engine. And when you do that, you end up with less mass, you end up with a more efficient engine. And so you cycle the design on all these parameters, and we ended up with an engine that's 35% more efficient. We call it HISITE, hydrogen, steam, injected, intercooled turbine engine, HISITE. And we recently demonstrated some of the hardest technologies associated with that. We demonstrated, number one, can we make a condenser that can survive under those conditions? Check. We did that. We used additive manufacturing. We were able to achieve that. Number two, can we capture enough water? And under the cruise conditions, we were able to achieve capturing 1 gallon every 3 seconds, which is more than adequate water to complete the cycle that I'm talking about. And number three, in our most modern combustors, the ones we have in our commercial state-of-the-art products today, we put in the same amount of water, and we demonstrated that we can get to 99.3% lower oxides of nitrogen, even then the improvement over the state-of-the-art engines burning 100% hydrogen. So there is hope. The challenge, of course, is there's no hydrogen available at the flight line ubiquitously today. Also of note is that hydrogen is not readily available. You have to make it. Most hydrogen, 99% of it, is made from fossil sources today. That hydrogen is typically used to make things like ammonia, and that ammonia is used for fertilizer. And for the synthetic aviation fuels, we never want to compete with food sources. Well, with crops, the same thing, you don't want to compete with the fertilizer. The last point, if I were to use 90% of the hydrogen that was produced last year, I would only power 10% of the commercial fleet.
Oh,
So,
wow.
huge, huge challenge.
Yeah, no, yeah, it's that gives a really good perspective of where we are and where we need to go. So so if hydrogen is further off, like what about alternative fuels such as sustainable aviation fuel or SAF?
So we work with SAF a lot. All of our engines are actually capable of running the 8 approved blends. There is an approval process. We and all the other original equipment manufacturers sit on that approval process. Sometimes it involves testing, and we do that testing. And the 8 pathways that are approved today, up to 50% blend, can be used in any one of our products. Furthermore, all of our modern products can operate on up to 100% SAF as well. And so we are SAF ready in our fleet, and we will continue to be ready. The challenge is that the commercial fleet last year burned of order 100 billion gallons of jet fuel. And the entire world only produced just a few 100 million gallons of SAF last year in the equivalent time. And so we need to ramp up the capacity, but that capacity is not even growing at the typical 3 to 3.6% cumulative annual growth rate of commercial air travel. And so really a step change would be required in order to get there.
Would the development of SAF, I mean, typically when you develop new things, they typically, they cost more in the onset, and then potentially over time, that number goes down. Would that help improve, for the typical airline passenger, would that help improve costs on their end? Because I know a lot of folks that would be listening, that do fly, that's kind of in the back of their mind is, the cost of airline travel and how expensive it is and may potentially become.
So I'm not going to speculate on the price elasticity, but there are airlines that will allow you, when you buy your tickets, to go on and essentially purchase SAF. SAF can be 2 to 5 times more expensive today, exactly because of the the challenge that you refer to, which is the virtuous cycle, that the manufacturing base doesn't yet exist and needs to be capitalized. There are also, and persists under the current administration, blenders tax credits and such that offset some of those costs, that allow to essentially bring together some degree of equalization. I think it's also important to note here in Connecticut, where after the closure of the Mira facility, where roughly half the trash in the state used to go, there are opportunities to take some of those waste streams and turn them into fuels such as SAF and home heating oil. And so we have opportunities here in the state, and many of us are working together through CASE and through our companies and institutions to realize some of those opportunities.
Thanks for that, Michael. I know our listeners, that's definitely a burning question in the back of their mind. So really appreciate you speaking to that. So to close, how would you sum up the outlook for the aviation and aerospace industry to anyone interested in flying, STEM, so STEMM, or an engineering career?
So my message to the science, engineering, technology, engineering, and mathematics, the future is bright. And when you think about all the new opportunities, starting with defending our freedom, the world has become much, much more dangerous. And so the importance of the military products, and be it the missiles or the aircraft, defending our freedom is a priority. When you think about the opportunities for more efficient aviation and the challenges that are before us, that is a huge opportunity for the future. And when you think about the new space economy, that is another huge opportunity. And even on the broader realm, at Collins Aerospace, we control about 2/3 of the air traffic in the world. Today, the United States and Europe are significantly investing in air traffic management solutions. And so there are solutions there. There's so many new opportunities, and these are really exciting, be it in established companies or the startups. The ecosystem is really healthy, and I would encourage all of you to consider a career in aerospace. I've spent my time doing it, and I could not be prouder that I've made a difference to the world with some of the technologies that I've helped introduce, and we've introduced at RTX and at Pratt Whitney.
Yeah, so folks, there's the opportunities there. You've heard it from one of the foremost experts in Connecticut and frankly in the world with respect to aviation. So please, stay tuned and keep your eyes peeled because there's certainly opportunity. So on behalf of all of us living in Connecticut and others tuning in from other states, thank you, Michael, for sharing with us information about the future of aircraft propulsion. You've given us a lot to think about. Listeners, I encourage you to subscribe to this podcast on Apple Podcasts, Spotify, Amazon Music, or YouTube, and visit the Academy's website at ctcase.org. To learn more about our guests, read the episode transcript, and access additional resources, as well as to sign up for the Case Bulletin. Michael, I can't thank you enough. I mean, you've really opened up a world of opportunity and a world of knowledge that people probably weren't aware of, and it's right here in their backyard. So thank you again.